So the next thing we are going to discuss more about covalent bonds. We know how covalent bonds are formed. They are formed by the sharing of electrons, right?
Yes, sir.
So what does sharing means? If I'm talking about sharing, it means when the two atoms sharing their electrons. So it means that they must have some space in common.
Yes.
And in that space they have electrons in it, and those electrons are to be considered as shared. So for that purpose, actually what happens that the atoms overlap their orbitals first. So the overlapping of the orbital occur, and the orbitals which have unpaired electron, because usually we see that, let's talk about carbon. Carbon has a 6 electron. Its electronic configuration is 1s2, 2s2, 2p2, right?
Yes, sir.
So if I fill the orbitals, it is going to be 1s, 2s, and 2p. So a pair of electron over here, a pair over here, and two unpaired electrons in these two pair orbitals, right?
Yes, sir.
So actually these unpaired orbitals overlaps with the orbital of another atom which has an unpaired electron. So as a result, both the atoms orbitals having unpaired electrons get overlapped, and as a result, a shared pair of electron is formed. Is this understandable?
Yes, sir.
Okay. So there are two types of overlapping. Either one is called direct overlapping or a linear overlapping, and the other one is called sideways overlapping or parallel overlapping. So whenever a direct or a linear overlapping occurs, it leads to the formation of a covalent bond. That specific covalent bond is called sigma bond. And this one is considered as a pi bond. The one which is formed by the sideways or by the parallel overlapping. Is this understandable?
Yes, sir.
Okay. So now, which orbitals you have to understand involved in the sigma bond? In sigma bond, either s orbital is involved. Beside s orbital, there are three more types of orbital: sp3 orbital, sp2 orbital, and sp orbital. So these are the orbitals which involved in direct overlapping and leads to the formation of sigma bond. Is this understandable?
Yes, sir.
Okay, we haven't studied these three orbitals yet. We are going to discuss these. Okay, we will be discussing these.
Okay, sir.
Now,
Okay.
and the other important thing over here is that when the two atoms interact with each other to form a bond, to form a covalent bond, sigma bond is the first bond that is formed between the two atoms. Is this clear?
Yes, sir. Because every atom has a s orbital, so the first one is always s bond.
Yeah, if either every atom has a s orbital, or if it is not has any s, then it has any one out of these three. Okay. Now, when the p orbitals overlap, they overlaps below and above this sigma bond when the sigma bond is formed, and they overlapped in a parallel fashion or a sideways fashion, and leads to the formation of pi bond. So remember, this pi bond is formed after the sigma bond. So after the sigma bond, whenever any other covalent bond formed between those two atoms who already have formed the sigma bond, that bond is called pi bond. Is this understandable?
Okay. Yes, sir.
Oh, okay. Now, have a look over here. As I have told you, whether there are s orbitals. So if there is a s orbital into the atoms, that is the case with the hydrogen, because when we talk about hydrogen has only s orbital in it, right?
Yes, sir.
So when the two hydrogen atoms covalently bond to form a hydrogen molecule, their s orbitals linearly overlaps or in a direct fashion overlap to give this kind of a shape, and that's what we call SS overlapping, and it leads to the formation of a sigma bond. Is this clear?
Yes, sir.
Now, as we have discussed that s orbital comes, hydrogen has a s orbital, but before the bonding, if the other element, which is the other atom which is going to form a covalent bond, is actually belongs to the elements from group 13 to group 17, then they are going to transform their orbitals into either sp orbital or sp2 orbital or sp3 orbital, which has a this kind of a shape, one lower lobe, one a smaller lobe, and one a bigger lobe. Okay, and these two are going to
Okay,
overlap
sir.
with each other like this, and as a result we got this shape. So this is also forms a sigma bond, but in this sigma bond a s orbital overlapped with any one of these orbital, and this is the case when hydrogen is actually bonded with any atom which is from the elements of group 13 to group 17. Is this understandable?
Yes, sir.
If you have any question, any query, any confusion, please ask.
This is only for when hydrogen is bonding, no other element.
No, see, this is the case when the two hydrogen atoms are bonding covalently.
Hmm.
And this is the
Yes,
case
sir.
when hydrogen atom is bonded to any other atom which is from group 13 to group 17. So it means that this orbital is from any element from group 13 to group 17, and this orbital is of hydrogen.
Okay, sir.
So it means in this here we have an example of hydrogen is bonded to carbon, or hydrogen is bonded to nitrogen, hydrogen is bonded to chlorine, hydrogen is bonded to oxygen, hydrogen is bonded to silicon, hydrogen is bonded to, let's say, boron. So with anyone with which hydrogen can form a covalent bond, that covalent bond is formed by the overlapping of the s orbital of the hydrogen and any one of the orbital from the elements of group 13 to group 17. Is this clear?
Yes, sir.
Okay, now if the covalent bond is going to form between the two atoms which are from group 13 to group 17, like a bond between carbon-carbon, a bond between carbon-chlorine, a bond between nitrogen-oxygen, a bond between, for example, chlorine and nitrogen, for example, a bond between fluorine and oxygen, for example, a bond between, let's say, nitrogen with sulfur, a bond between sulfur with oxygen. So any element, any two elements from group 13 to group 17, which are going to bond covalently, they modify or transform their orbitals into any one out of these three, and whichever, whether it's sp, whether sp2, whether sp3, its shape is going to be like this, and both the atoms are from group 13 to group 17, so they form the orbitals, they transform their orbitals into shapes like this, and they are going to overlap linearly. So as a result we got this shape and a sigma bond is formed. Is this clear?
Yes, sir.
If you have any confusion, any query, please ask.
No.
Okay. Now, after this, see here, it's the first bond between the two atoms, which I highlighted with the red, right?
Yes, sir.
So this one is the sigma bond. So when the sigma bond is formed, and if the two atoms have to form a double bond or a multiple bonds with each other, so what happens? Now, this is their p orbital, and this is the p orbital of the other atom, right?
Yes, sir.
So as linear overlapping took place over here in the middle, so they the p orbitals does not bond in linear fashion. They are actually, if you see, they are parallel to each other, isn't it?
Yes, sir.
So they are going to overlap with each other parallelly from above the pi sigma bond and below the sigma bond, as you see over here. The two lobes of the two p orbitals overlapped above the sigma bond over here and below the sigma bond over here, and these two overlapping are going to contribute to give you a one pi bond. Is this understandable?
Wouldn't this also be linear because they're both getting into a horizontal after bonding.
Yeah, after the bonding, they are getting horizontal, but before the bonding, if you look at their orientation, they are exactly parallel to each other. The linear would be this one. For example, see, this is
Yes.
the p orbital and this is the 1p orbital, right? And
Yes, sir.
the p orbital. If the two p orbitals overlap in this way, then it is considered as linear.
That would be the bonding that we just did on the left
Ah.
side, the
Yeah,
last one.
left side that leads to form a sigma bond. And in sigma bond, if you see, there is no p orbital which is involved in the sigma bond. In sigma bond, either s orbital is involved or these orbitals are involved.
Yes, sir.
And if you see over here, this is one p and this is another p, right? So
Yes, sir.
after overlapping, their lobes from the top gets overlapped and their lobes from the bottom gets overlapped in this way. That the green clouds actually representing these two. So that's why we call it sideways overlapping or parallel overlapping. Understandable?
Yes, sir.
Okay.
And a double
Double
bond
formed.
forms.
First bond is already there. This
Yes, sir.
electron cloud and this electron cloud will leads to the formation of a second bond over here. Is this clear?
Okay. Sir. Yes, sir.
If you have any query, any confusion, any question, please ask.
No.
So over here, there is a one sigma bond and one pi bond, right?
Yes, sir.
Okay. Now it's for you. Now for the first one, can you tell me how many sigma bonds are there and how many pi bonds are there?
Seven sigma bonds, no pi bonds.
7 sigma bonds and
No pi bonds.
very good. So if you see, first one has 7 sigma bonds and no pi bonds, right?
Yes, sir.
Now for the second one,
Five sigma bonds, one pi bond.
5 sigma bonds and 1 pi bond. Okay. Good. Now for the third one,
What does the triple one represent? How many pi bonds, how many sigma?
what was the condition for the sigma bond?
The first one would be the sigma bond.
Yeah, so between
It
among
needs
these three, how many are the first one?
two.
No, between the three, if I see there is a carbon and
Only
hydrogen.
talk about carbon and nitrogen.
Yeah, I'm talking about carbon and nitrogen. There are 3 bonds. Among 3 bonds, how many are the considered as first one?
Only one,
Only one.
the middle one. Yes.
So how many pi bonds are there in this molecule? How many sigma bonds are there in this molecule?
Two sigma bonds, two pi bonds.
Very good. So 2 sigma bonds and 2 pi bonds. Is this clear?
Yes, sir.
Any confusion?
No.
Okay. Now, this is the electronic configuration of carbon. Okay, tell me how many
Yes, sir.
bonds a carbon atom form?
It has 4 electrons, valence shell, 4 bonds.
4 bonds a carbon atom form, right?
Yes, sir.
Now, see, right now, if I show its electrons in the outermost shell, they are going to be arranged in orbitals in such a manner, right?
Yes, sir.
So if you recall, 2s is going to be a sphere.
Yes, sir.
Okay. Now, 2py is here on the top and on the bottom. 2px is on the right and on the left, and 2py, 2pz is on the front and at the bottom, right?
Yes, sir.
So a pair of electron is over here in 2s, and one electron in 2p, and one electron in 2p, 2py, and one electron in 2px, right? So how this s orbital is going to overlap? Are you getting my point?
No.
This s orbital is a small ball in the middle, which is, covered by the 3p orbitals. So it means that this is not going to get approached or overlapped by the orbital of any other atom, because it has a lower energy and p orbital has a higher energy. So in this ground state, carbon can only able to share its 2 electrons only, not the all 4. Is this understandable?
Yes, sir.
And see, that's what
To
happens in
share.
carbon monoxide. If you open the dot and cross diagram of carbon monoxide we done in dative bonding, carbon is sharing its only 2 of the electrons and one lone pair stays, and oxygen is sharing a pair to complete the octet of carbon.
Yes, sir.
So that's what happened in carbon monoxide. So see, but we normally see that in most of the cases, carbon is forming 4 bonds, isn't it?
Yes, sir.
So it
Is it
means,
because it's reaching an excited state and one electron
yeah,
from 2s is going to 2p?
yeah. So first it is going to be very good. It is going to be go in the excited state, right?
Yes, sir. Yes, sir.
Okay. Yeah. So in an excited state, see, we now got 4 unpaired electrons. So it means can carbon form 4 bonds?
Yes, sir.
No. Still, the problem is not solved, because if you recall the previous shape, when it gets excited, still it has a 1 electron in its p, right?
Yes.
So now carbon has 3 electrons in actually in the outer orbitals, which can overlap by the other atoms, but carbon doesn't have any, the 4th electron is actually hindered or, protected by those orbitals. So that 4th electron is not going to be shared. Did you understand this
Which
point?
is in the s orbital.
Yeah, which is in the s
Yes.
orbital. S orbital has a lower energy.
Okay.
So still the problem
Okay.
is there. Are you getting my point?
Yes, sir.
So what happens? See, this is the problem. That's what I am telling you. There is a 1 electron in 2s, which is still after the excitation hindered or protected by the other orbitals. So as a result, the carbon is still not going to, after the excitation, it is still not going to share its 4th electron. The 4th electron, the s orbital is not going to be overlapped by the orbital of any other element. Is this understandable?
Yes, sir.
So see, that's what happened. Just read it very carefully. Then I will be discussing this.
Okay, sir. I've read it.
Please. Yeah. So what happens? A hybridization occur. Hybridization, we know it means mixing, right?
Yes, sir.
So we have a 1s orbital which has a lower energy. So that 1s orbital and the 3p orbitals mixed together, which we called hybridized together. So see how many orbitals actually hybridized with each other?
4.
4. So as a result, four new orbitals are formed, which we called molecular orbital or hybrid orbital, and all of them are having a same shape, size, and energy. And that's why we call them sp3 orbitals, because there is a one s orbital in those molecular orbital and 3p orbitals. Is this understandable?
Yes, sir.
Okay. Now, look, that's what. See, the y-axis is representing the energy over here. So this is the s orbital. This is px, this is py, this is pz, right?
Yes, sir.
So after hybridization, what happens? S orbital is actually divided into 4 parts, and each part is oriented over here to contribute to each new orbital. In the same way, p orbital is broken down into 4 equal parts, and each part is bonded or is actually, joined with the 1/4 part of the s orbital. In the same way, that same happens with the py orbital and the pz orbital. Each of these orbitals flipped or broken down into 4 equal parts, and one part from the each orbital gets connected with each other to form a one new orbital, and that's why each new orbital has a same shape, same size, and same energy, because they all have a same components. Is this understandable?
Yes, sir.
Okay. So see, that's what happened. See that if you see this sp3 orbital has a one bigger lobe and a one smaller lobe, right?
Yes, sir.
So carbon is initially the orbitals are arranged in this way, but when the hybridization occur, these 4 sp3 orbitals are actually joined in such a way that this from this point they actually got joined with each other. Okay.
Yes, sir.
So as a result, they get oriented in this shape, and see the smaller lobes are actually in the middle over here. Now see, if you see what kind of shape they are forming, you have studied in shapes. Can you recall this shape?
Uh, this is trigonal
How it is
hammer,
triangle?
pyramid,
How many angles you are getting?
4,
So 4.
3.
No, there are 4.
No,
1,
4.
3, 4. Right now you are saying 4. So if there are 4, which shape it was, if you recall, there are 4 bond pairs now. It means C. Okay, let me make it clear.
Tetrahedral, 4.
Yeah, tetrahedral, because 4 bond pairs, 4 lone pair, 4 unpaired electrons are there. So it is going to make 4 bond pairs. So the shape is tetrahedral of sp3 orbitals. Is this understandable?
Yes, sir. Yes,
So
sir.
now what happens that the carbon atom is initially before the bonding it's this shape, but when it has to make a bond and become a part of the molecule, it will get hybridized and transformed into this shape. Now this is going to see over here. Now this carbon is going to be take part in the bonding. Now if you see, this orbital is overlapped by one s orbital of hydrogen. So a sigma
Yes,
bond
sir.
is found between carbon and hydrogen. Isn't it a direct bonding, direct overlapping?
Yes, sir.
It is, isn't it? This is the case, right?
Yes, sir.
That we have studied earlier. So the same thing is happening over here. A second sigma bond. A same thing is happening over here. So a third sigma bond. And the same thing is happening 4th time. So the 4th sigma bond. Is this understandable?
Yes, sir.
Now have a look at methane. See, both the carbon atoms first form sp3 orbitals, then one of its sp3, this is the case, if you see, which I have highlighted, this is this case.
Yes, sir.
Is it understandable or not?
Yes, sir.
And here the s orbitals are overlapping with each other, so it is the second type of linear overlapping where we have discussed one s and one sp, one sp2 or sp3 orbitals gets overlapped with each other, right? So till here
Yes,
is
sir.
clear.
Yes, sir.
Okay,
But
now
all of this is for only SP3, right?
yeah, these all are the cases are sp3. Now read the note.
See, you know, I have all experiments. Okay. Yes, sir. I read the note.
Yeah, sure. Okay. So in all of these cases where carbon, nitrogen, and oxygen have all sigma bonds, oh sorry, yeah, all sigma bonds, then in those compounds, carbon, nitrogen, and oxygen are sp3 hybridized. For example, if I talk about H2O, oxygen has how many sigma bonds?
Two.
Two. So if oxygen has a two sigma bonds, and do oxygen have any pi bond over here?
No.
So it means oxygen has sp3 hybridized, okay?
Yes, sir.
So have a look at these cases. In all of these cases, nitrogen, and if here I have underlined oxygen, and in this I have underlined carbon and oxygen. So see, carbon has all sigma bonds, and oxygen also has all sigma bonds. There is a no pi bond with oxygen. There is no pi bond with carbon. In ammonium, nitrogen has all sigma bonds. In N2H4, each nitrogen has all sigma bonds. In ammonia, nitrogen has all sigma bonds, right?
Yes, sir.
So if this is the case where the carbon, nitrogen, or oxygen atom has all sigma bonds, then that carbon, oxygen, and nitrogen are sp3 hybridized. Is this clear?
Yes, sir. So they all be forming the shape above.
Yeah, but in each case the electron geometry is tetrahedral, but it is not necessary the shape would be the tetrahedral. For example, if I talk about ammonia, ammonia has a one lone pair as well. So nitrogen atom also form tetrahedral electron arrangement, but in one orbital it has a pair of electron, right?
Yes, sir.
So only overlapping took place in these three regions.
Okay.
So it makes the electron geometry is still tetrahedral, but shape is going to be pyramidal because there are three bonds which are declined from the nitrogen. Are you getting?
Yes, sir.
For example, if I talk about oxygen of a water, it forms the electron geometry of tetrahedral, but it has a two lone pairs. So
Yes,
overlapping
sir.
only take place with the two orbitals, making the structure bent. The electron geometry is, that's why the electron geometry is tetrahedral. Is it
Okay.
understandable?
Yes, sir.
Okay. Okay. Now to understand this, I have one more thing to show. Just give me a minute. I am looking where it is. Where is chemistry?
Hello.
Now what you are seeing on the screen?
Hybrid orbitals.
Is it a video?
Yes, sir.
Okay. So 1 minute, let me see whether
Hello, and welcome to a video about hybrid orbitals, often called valence bond theory, developed in
now tell me, are you listening the voice as well?
Yes, sir.
Okay, that's fine. So do listen it carefully, then we will discuss, okay?
the 1930s by the great
Yes,
chemist
sir.
Linus Pauling as a model of bonding to understand the three-dimensional placement of atoms in a molecule, and that is critical to our understanding of the properties that molecules have.
Sir, your screen has
In this
glitched.
video, we will look at methane, ethene, ethine, ammonia, and water as our models for hybridization.
1 minute.
Sir, your
Only
screen
a
has
One
small
minute,
glitched.
yeah,
group of
yeah.
atoms in the second period that the model really works for, but among those are carbon, nitrogen, and oxygen, which make up
1 minute. Now is my screen is sharing?
Yes, sir.
Okay. Why it is resume pause? No, okay, if I'm making it a bigger. Now I'm starting from the start, okay?
Yes, sir.
Hello, and welcome to a video about hybrid orbitals, often called valence bond theory, developed in the 1930s by the great chemist Linus Pauling as a model of bonding to understand the three-dimensional placement of atoms in a molecule, and that is critical to our understanding of the properties that molecules have. In this video, we will look at methane, ethene, ethine, ammonia, and water as our models for hybridization. There is only a small group of atoms in the second period that the model really works for, but among those are carbon, nitrogen, and oxygen, which make up the vast majority of molecules that exist on Earth. So the model applies to a limited number of elements, but it applies by far to the majority of molecules. Let's take a look at the word hybrid. It is a blending of two varieties. If you get a horse and donkey together, you get a mule, a blending or hybrid of a horse and a donkey. Let's get to hybrid orbitals using carbon as our model.
Okay, tell me till here, did you understand the basic concept?
Yes, sir.
Okay.
As a single atom, not bonded to anything, carbon has 2 electrons in 1s, 2 electrons in 2s, and 2 electrons in 2p. This electron configuration is the energy arrangement of carbon's electrons. However, carbon rarely exists in nature as an individual atom, except momentarily while undergoing chemical reactions. Carbon exists with its valence electrons bonded to other atoms. When carbon bonds to 4 other atoms, carbon's 4 bonds are experimentally seen to be equivalent. And so when the carbon atoms finds itself in a bonding situation, its bonding electrons themselves exist at equivalent energies, which requires that they hybridize to an energy that is intermediate between the 2s energy and the 2p energy. Or you can think of it as a blending or hybridization of the two energies, the s and p energies. And since the energies of these electrons have now changed, the shape of the orbitals they occupy are different as well, which we will see momentarily, and those are called hybrid orbitals. They are named 2sp3 hybrid orbitals. The naming often trips up students, so before we go any further, let's take a look at where the 2sp3 name comes from. The 2 comes from the second principal energy level that the valence orbitals are in. The S comes from the 2s orbital contributing to the hybridization, and the P comes from the 2p orbitals contributing to the hybridization, and the 3 comes from the number of 2p orbitals used in the hybridization.
Did you understand?
Yes, sir.
If you have any confusion and any query, please ask.
Okay, sir.
Okay.
Once hybridized, the 2s and 2p orbitals no longer exist, and so we have 4 2sp3 hybrid orbitals. 4 2sp3 hybrid orbitals derived from combining the energies of 1 2s orbital and 3 2p orbitals, which gives a total of 4 2sp3 orbitals. Before we look at the shape of hybrid orbitals, it would be helpful to briefly review the atomic orbitals. The 1s orbital is a sphere, the 2s orbital is a larger sphere surrounding 1s. And here we will get rid of 1s since we are only concerned with the valence electrons. Each 2s orbital is a 2-lobed shape converging at the nucleus. So there are the 3 2p orbitals. However, when hybridization occurs, the s and p orbitals cease to exist, and the 2sp3 orbitals have an entirely different shape. We can see that orbital hybridization explains the VSEPR placement of carbon's 4 valence electrons, since all 4 2sp3 orbitals are equivalent. Each 2sp3 orbital repels the others with equal force, resulting in identical bond angles.
If you're a web designer, here are 4 Wix Studio features you gotta know.
The carbon atom only hybridizes when it is.
So I hope till here it's clear to you.
Yes, sir. Only one question.
Yeah.
When the s orbital and the p orbitals both cancel out only in bonding, and they come back when it's all bonded.
Can you repeat your question?
When bonding occurs, the 2 sp3 orbitals are formed.
Yeah,
So
formed
the
by the
2s
mixing
and
of s and p orbitals. Yes.
yes, so the s orbital and the p orbital are gone because they are hybridized.
Yeah.
But-
Now they are not there. They vanished. They transformed into these new orbitals.
So these orbitals exist from now on in that specific
Yeah,
carbon
yeah.
atom.
If so, for example, if methane is formed, we see that methane has a 4 bond pairs, and if there is a 4 bond pair, so the shape is 109, the tetrahedral, and the bond angle is 109.5, right?
Yes, sir.
So if this shape is there, if this molecule is there, so in this molecule, the carbon has this sp3 orbitals now onwards. It doesn't have now s and p orbital. S and p orbital are there only when the carbon atom is alone. It's not bonded.
Okay, sir.
Okay, but when it forms a bond and it turns into a molecule, and in that molecule, you are observing that carbon has a 4 unpaired electrons or 4 bond pairs. So it means that now the carbon is sp3 hybridized. So it means that in this, that carbon has now no s and p orbitals from the 2 or from the second shell. Instead, it has a 4 sp3 orbitals.
Okay, sir.
Is this clear now?
Yes, sir.
Is in a bonding situation. Here, 4 hydrogen atoms bond to carbon by overlapping their orbitals with carbon's hybrid orbitals. So what would be the reason for this? If we go back and see that both carbon and hydrogen have unpaired electrons, the overlap allows the electrons to pair and thus go to a lower potential energy. The illustration here contains the valence electrons of both carbon and hydrogen. And since everyone likes to visualize atoms as spheres, we can do the same. Here is our carbon atom, and here are the hydrogens with the overlapping spheres, indicating the overlapping orbitals that constitute the bond. The bonds are more readily discernible in a ball and stick model, which also makes the bond angle more visible. Since all 4 sp3 orbitals are equivalent, each bonding orbital repels the others with equal force, resulting in identical bond angles. The bonds in hybridization also have their own nomenclature. The overlapping orbitals are called sigma bonds, which represents the single bond occupied by a single pair of electrons. What about double bonds? How does the hybridization model explain double bonds?
Okay, before heading from here onwards, just recall when a double bond, when there is a double bond, which kind of overlapping would occur?
Pi bond.
Yeah, pi bond is
One
formed.
pi bond, one sigma bond.
Yeah, very good. A pi bond is formed. That pi bond is formed by which type of overlapping?
Parallel overlapping.
Parallel overlapping. And parallel overlapping is done by which orbital?
P orbital.
P orbital. Now, in the previous case, we have seen all three p orbitals are actually, got involved in the hybridization, and as a result, we got sp3 hybrid orbitals, right?
Yes, sir.
So is there any p orbital left at that moment?
No.
So it means that if the carbon is sp3 hybridized, it would not able to do the parallel overlapping and form a pi bond. Are you getting my point?
Okay, so it won't be able to form a double bond.
Yeah, which carbon? If the carbon is sp3 hybridized,
Okay.
because that carbon has no p orbital left.
Okay, sir.
Is this clear?
Yes, sir.
Okay, now see this.
We will use ethane C2H4 to see what happens in a double bond. The single bonds we know are sigma bonds, and the double bond also has a sigma bond, but the second bond of a double bond is a pi bond. Let's see how hybridization and orbital overlap can explain a double bond. The two carbon atoms in ethane are equivalent, so let's look at one of the carbon atoms first. A pi bond comes from the
So see, this is the case where the carbon is initially, when it's an atom, it has a two s orbital and two p orbital, right?
Okay, sir. Yes.
So from that, excitation occurs. After the excitation, hybridization occur, right?
Yes.
overlap of unhybridized p orbitals. And so the atom hybridizes.
So see, now in this case, what happened? How many orbitals, how many p orbitals got undergo hybridization?
Only two.
Only two. That's why the new orbital is called sp2.
sp2 because only two from the p orbital.
Yeah, and one from the one s and two p orbital. So there are in total three orbitals got hybridized, and that's why we got three new orbitals which are hybrid.
Yes.
And you see
Yes,
the
sir.
p is still there now, right?
Yes. It hasn't vanished. Yes.
Yeah. So it means now in this case, it can form a pi bond because it has a p orbital.
Okay.
Only three orbitals, leaving a p.
So see, this is how it happens. If you see, the p orbital is the blue one,
Yes.
and the sp2 orbitals are the green one.
Yes, sir.
Okay, if you remove the blue p orbital,
Yes.
what will be the orientation or shape of the three sp2 orbitals?
There was a three bond pairs. So trigonal planar.
Trigonal planar. So what was the bond angle between these?
120.
120. And if you are observing right now, p is exactly perpendicular to these three sp2 orbitals, right?
Yes, sir.
So what is the angle between p and sp2?
90.
90 degree. So that's why if you see, the lobe which is on the left gets overlapped with another this kind of a lobe. So the both p orbitals are exactly parallel to each other.
Yes, sir.
And then when they are parallel to each other, they can easily undergo sideways or a parallel overlapping.
Yes, sir.
Are you able to visualize the things which I am telling you?
Yes, sort of.
Yeah, sort of. So now you will watch this in the video. So I hope that it will make more clear. Things will be more clear, inshallah.
p orbital unhybridized for the pi bond. The hybrid orbital is called 2sp2, the superscript 2, denoting that only two 2p orbitals have contributed to the hybridization. The 2sp2 hybrid orbitals exist in a plane perpendicular to the unhybridized 2p orbital. Let's remove the 2p orbital for now to more easily see that. The 2p hybrid orbitals are spread out at a 120-degree angle, which means that they exist in a plane, and the plane is perpendicular to the unhybridized 2p orbital. So this is what both carbon atoms do when bonding occurs in ethane. Each carbon atom is sp2 hybridized. The sigma bond occurs with 2sp2 orbital overlap. What about the pi bond, the second bond of the double bond? Previously, we said that it comes from the unhybridized p orbitals, which we see here from both carbon atoms. The top and bottom lobes of the 2p orbitals overlap above and below the axis of the sigma bond, forming a single pi bond, the space in which the now paired electrons move around. The ball and stick model shows this double bond with two dashes. To summarize, sigma bonds occur along the axis between nuclei. The pi bond occurs above and below the sigma axis, where the p orbital lobes have overlapped.
Now see, this can be the question from paper 1 as well. Sometimes examiner asks to know how student understand the bonding about the axis. So you must remember that whenever a sigma bond is formed, the electrons which are involved in the sigma bond is exactly on that axis where the nucleus of both the atoms are there. You are seeing the line crossing through the sigma bond, right?
Yes.
That is,
Yes, sir.
and on both the ends of this line, there are nucleuses. So
Yes, sir.
the electrons which are involved in the pi bond are exactly on the axis where the nucleus of both the atoms are there. And is this clear?
Yes, sir.
And the electrons which are involved in the pi bond are above and below that axis or above and below that plane where the sigma bond and the nucleus are existing.
Yes, sir.
The ethane molecule also bonds to 4 hydrogen atoms by overlapping with both carbon's other 2sp2 hybrid orbitals, creating 4 more sigma bonds. In the ball and stick model, we can readily see that each carbon has a trigonal planar geometry, and thus the whole molecule exists in a plane with a single pi bond above and below that plane. Now let's look at how hybridization can be a model for the triple bond using ethine.
So see, now you see how many pi bonds are there?
There are 2 pi bonds.
So it means how many carbons p orbitals are left unhybrid?
2. So only one will be hybridized from the p orbital.
So which kind of hybridization this carbon will do?
sp.
sp. So see, it's very simple. If you got the key concept that if carbon has all sigma bonds, it's for carbon, nitrogen, and oxygen, all 3. If they have all sigma bonds, then it means that they are all s and p orbitals involved in the hybridization. So that carbon, nitrogen, and oxygen has sp3 hybridization. If the
Yes, sir.
carbon, nitrogen, or oxygen has a 1 pi bond, so it means there 1 p orbital left unhybrid. So that carbon, nitrogen, or oxygen undergo sp2 hybridization. And if the carbon, nitrogen, or oxygen has a 2 pi bonds like this,
Yes,
so
sir.
it means that carbon, nitrogen, and oxygen has 2 p orbitals left unhybrid. So in that case, that carbon, nitrogen, or oxygen undergo sp hybridization. Understandable?
Yes, sir.
C2H2. The carbon hydrogen bonds are sigma bonds, and the triple bond is 1 sigma bond and 2 pi bonds. Let's see how hybridization can accommodate this. Since pi bonds come from p orbitals, and we need 2 pi bonds, then 2p orbitals have to remain unhybridized, and so the remaining single 2s orbital and a single 2p orbital will hybridize to 2sp hybrid orbitals.
So see, 1
And
p or
there's also the violet.
so see, 1 p orbital and 1 s orbital undergo hybridization to form 2 sp orbitals, which you are seeing with the green lobes.
Yes, sir.
And the blue one and the violet one are the unhybrid p orbitals.
2px.
Yes, sir.
And the blue 2py orbitals. Here, each green lobe's a single orbital, and so they each have an electron, while both violet lobes constitute the single 2px orbital with a single electron, and both blue lobes constitute the single 2py orbital with a single electron. The other carbon in C2H2 also has that same triple bond, and so it has the same hybridization. Let's see what happens during bonding. sp orbitals from both carbons overlap, forming a sigma bond. The upper lobes of the blue 2p orbitals overlap, as do the lower two lobes, creating the first of the two pi bonds. Can you guess where the second of the two pi bonds comes from? Yes, that's right. It is the overlapping of the violet 2p lobes.
So see, one p orbital is below and above, so they overlap from the top and the bottom of the sigma bond. And the other p orbital is actually in front and
Front
back.
and back.
Yeah, so they overlap from the front and back to make the other pi bond.
Let's get rid of the sigma bond for a moment to take a look at something interesting. Each pi bond lies on a separate plane, and the two planes are perpendicular to each other, and so the two pi bonds are perpendicular to each other. Finally, two hydrogens will overlap with the remaining sp hybrid orbitals, creating the C2H2 molecule. The overlap of the space-filling model reflects the overlapping orbitals, which is also represented by the ball and stick model. In the remainder of the video, we will look at hybridization of nitrogen and oxygen using NH3, ammonia, as our model for nitrogen hybridization, and H2O, water, for our oxygen model. In NH3, nitrogen has 3 sigma bonds and a lone pair. So how does hybridization account for this? The hybridization is 2sp3, and nitrogen has 5 valence electrons, so one of the 4 2sp3 hybrid orbitals has a pair of electrons. The 3 sigma bonds come from the sp3 orbitals with a single electron, so they can pair up, and so the remaining electron pair is a lone pair, an unbonded pair of electrons. As with sp3 hybridization in carbon, nitrogen's hybrid orbitals spread out in a tetrahedral shape. And lastly, water. Here, oxygen has 2 sigma bonds and 2 lone pairs. In water, oxygen is also 2sp3 hybridized, but with 6 valence electrons. 2 of the sp3 orbitals have paired electrons. You can probably guess that the sp3 orbitals with a single electron will overlap with hydrogen, and the remaining 2 pairs are unbonded. They are lone pairs. Again, oxygen's hybrid orbitals spread out in a tetrahedral shape.
Okay, so I hope things are clear to you, or if not, please tell
Yes,
me.
sir.
Any query, any
They are
question,
clear.
any doubt? Yeah.
They are clear, but in nitrogen, oxygen, how a double bond and a triple bond is formed?
Okay.
Could you
If-
send me the link of this video so
Yeah,
I
yeah,
can
sure.
watch it
I
again?
will be sharing this link, and I will be sharing another link, and I will explain you how a double bond and a triple bond is formed in nitrogen and oxygen. Just wait.
Okay, sir.
Okay. Read the subtitle. Okay, if I just got a little back, they are saying oxygen, again, oxygen's hybrid orbitals spread out in a tetrahedral shape. So see, they are talking about the orbitals of oxygen that are tetrahedral, right?
Yes, sir.
But if we come to the shape of the molecule, as we have told you that we are going to ignore the lone pairs when we are making the shape, we consider it as a bent only because there are 2 atoms. And lone pair
Yes, sir.
is significant to find the bond angle, as there are 2 lone pairs, which causes more repulsion. As a result, the bond pair come closer to each other. So the bond angle is decreased to 104.5 from 109.5, right?
Yes, sir.
Okay.
Shape. That's it for hybridization, the product of a mad scientist. See ya.
Okay, I will be sharing this link with you.
Sir, I have another question.
Yeah.
Do they ask us to draw the shapes in paper
No,
too?
no, no. They don't ask you to draw the shapes. Which shapes? First tell me which shapes you are inquiring about.
I'm talking about the orbital shapes because there are so many and different kinds.
Yeah,
Do they
no.
ever ask us to draw it?
They ask you to show the overlapping, not the
Okay.
whole complete shape.
Okay.
The shapes which we discussed in the valence shell electron pair repulsion,
Yes.
those shapes has been asked to draw. But from
Okay.
here, they just ask you the shapes which you have seen when I have discussed you the sigma bond and the pi bond.
Yes.
Those shapes have been asked to draw, that how the overlapping show the electron cloud after the overlapping.
Okay, sir.
Okay. So I'm sharing the link of this video with you. Have you got it?
Yes,
Note
sir.
it down somewhere. I have
Yes,
sent
sir.
it in the chat. Okay.
Yes,
And
sir.
I am sharing one more link, and it is also very good to understand, the concept of bonding. Let me see if that's the one.
And we're back. The team is looking down the barrel of a 4:55 meeting.
Understand. And it's
Yeah. So I'm sharing one more link with you.
Yes, sir.
I hope you got it.
Yes, sir.
And there is one more link. So, yeah, your question. Let me move to your question. Okay, so here we have sp2 hybridization. That's what we have discussed earlier, right?
Yes, sir.
Okay, so, and we have seen the example of ethene.
Yes, sir.
Okay, so they don't ask you to draw the shapes like this. Okay, they ask you to draw the shape like this or these shapes, which is over here. These ones you have to draw actually these one.
Okay.
And for pi bond, we have to draw like this. Okay.
Okay, sir.
Okay. So see, if carbon, nitrogen, or oxygen have one pi bond in their compound, so then that carbon, nitrogen, oxygen is sp2 because one of the p orbitals left unhybrid. That's what we discussed. So if you see,
Yes.
for example, if I take the example of nitrogen, it's a okay. Let's have a look at the example of oxygen. Oxygen has a one pi bond, right?
Yes, sir.
So it means that oxygen is sp2 hybridized.
Yes.
So it means if it's an sp2 hybridized, so 3 orbitals are hybridized and p orbital is still left unhybrid like this.
Yes, sir.
So the other oxygen atom will have the same hybridization. So these are the p orbitals. Okay, so this one has a one unpaired electron and this one has a one unpaired electron. So they makes a bond, right? Oxygen has two
Yes.
lone pairs. So see, each oxygen has a two lone pairs. So these lobes which are on the right and on the left does not able to overlap any other orbital because these orbitals are completely filled, right?
Yes, sir.
This one has a one electron and this one has a one electron. So what will happen that when this is formed and these one have the unpaired electron, so from here you can make this the electron cloud like this and make the electron cloud like this.
Okay, sir.
So this is the oxygen double bond.
Okay, sir.
So for a pi bond, whether it's oxygen, carbon or nitrogen, the orbitals are like this only. The only difference is that in carbon,
Yes, sir.
all of them has a one unpaired electron. This is the case of carbon. Okay.
Yes,
And if it's a nitrogen,
yes, sir.
so in nitrogen, if nitrogen is making a pi bond, its shape is like this. It has one unpaired electron over here, one unpaired electron over here, and one unpair over here, because from here it has to make the pi bond, right? And one of the
Yes, sir.
hydrogen has a pair of electrons, so which do not take part in any overlapping.
Yes, sir.
And for oxygen, the sp2 orbital, it has to make a 1p orbital. Oh, sorry, one pi bond. Its shape is like this: one unpaired orbital in sp2, one unpaired orbital in over here, py,
And 2 lone pairs.
and 2 lone pairs over here.
Yes, sir.
So for carbon, oxygen, and nitrogen, the orbitals, the molecular orbitals after the hybridization, the shapes are exactly same. The only difference is the number of electrons present.
Okay, sir.
And here we have a sp hybridization when 1s and 1p orbitals mix. So the 2p orbitals left unhybrid, and due to this, they will form 2 pi bonds. So see, the shape would be like this. This black is one sp orbital, and this black is another sp orbital. This is whole one p orbital, and this is whole other p orbital. But one is at the top and bottom, and one is at the front and the back, right?
Yes, sir.
So see, that's what I try to make it visualize it, how after the overlapping, the electron cloud would be at the top and the bottom, or at the front and the back of the central atom, or the pi bond,
Yes.
or the sigma bond.
Ye-
Till here, is this
Yes, sir.
clear?
Yes, sir.
Okay, so till here we are done with the bonding. Now we are going to have a next class on Monday, right? So I want
Yes,
you
sir.
to
Inshallah.
go through all the notes, all the videos I have shared, and I just a minute. Okay. So we will be doing the past papers of the bonding in the next class.